Quantum information processing rests on very fascinating concepts, which are very powerful but also very special. We do not see them in every system. When we want to translate them into physical reality, we need to identify suitable physical platforms. And there we have two principal expectations, namely that these behave as genuine quantum systems, which generally means that they are very well isolated, but also that we can manipulate them very easily from the outside. And this is of course where the challenge arises, because these are two clearly competing objectives. So we need some guidance for the physical requirements on these systems, and this indeed exists in the form of the so-called De Vincenzo criteria. These include 5 main requirements, which are all very natural, and so let me first list these. Namely that we have well-defined quantum bits, that we can initialize in pure states, then we need a suitable set of gates, and in principle a universal set of gates. When we want to have a quantum computer that is of general purpose. Then we need to be able to read out this information by measurements, and to be again very general, we need to be able to do this on any of the quantum bits. And finally, none of this will ever be perfect. This is really an inherent aspect of quantum information, and therefore we need to have a specific idea of how precise we need to be. And for a quantum system, this all amounts to having a long decoherence time. So these are the main criteria, and they're indeed all very natural. But let us expand on them a little bit, and let us start with the quantum bits. For these quantum bits, what we really need to have is well-defined quantum systems with discrete states and this could be a certain number of states, but the most ideal case is indeed that they just have 2 states. And this simply arises when one combines this with the other criteria, in particular when one wants to implement the gates and manipulate the information in a reliable way. And one reason is that we can then have lots of identical systems with these 2 states, and just one characteristic energy spacing between the two that could in principle also vanish. And where these states arise from, well, this really depends on the physical system that we are considering, and so I will come back to this at the end when I give a few examples. So let us move on to the initialization of the system in pure states. This is essential so that we have maximal information about the state of the quantum system at the beginning of a calculation. And this can be achieved in several ways, for instance by carrying out a complete measurement on all the quantum bits in the system. But we could also, for instance, take a system and couple it to the environment very strongly so that it loses all its energy and goes into the ground state. So we can use measurements, or for instance we can use relaxation. But both mechanisms, measurements and relaxation, require us to couple the system very strongly to the environment. Whilst when we want to operate on the system during the calculation, we want to have it very well isolated. So we want to apply all these gates, and they must be all well defined, which again depends on the particular type of physical system. But we want to have control about this quantum system now from the outside, while still leaving it in a well-defined quantum state. So basically this means that we want to have well-defined control about this system. So this is what we really want to have during the calculation, and when we come to the end we want to read out the result, and there we need to have again some very well defined coupling to the measurement apparatus. And what well-defined means in all of these cases, for all of these operations and steps, is really quantified in this final point down here. And in order to quantify it, one best thinks about this problem in the following way. We know that errors are completely unavoidable in quantum computation, but we also know that we have some ways to mitigate for them, for instance by error correction schemes. Error correction involves additional physical components, quantum bits, as well as additional steps in our calculation. And so there should be a certain threshold for the precision of all these operations, that when we are better than this, the system should not become worse, but better when we include all these additional components and steps. And this one can indeed estimate, and this was one of the key points when one drew up these criteria. And what one then concludes is that one needs to be able to carry out round about 10 to the 5 operations on a single quantum bit during the time that it really behaves like a quantum system, so within one decoherence time. Now this is clearly very challenging because it tells us that we need to have a very well-defined quantum system, but we need to be able to manipulate it from the outside during the initialization, for the calculations, as well as for the measurement readout. On top of this, when one looks at the details, for instance for the 2-qubit operations, one needs to have some internal interactions that one needs to be able to switch on and off. To see how this can be addressed in practice, let us briefly look at some candidate systems where we focus on their strengths and weaknesses. This is a very incomplete list of systems which I put into just a pedagogical order. So this does not indicate any personal preference or judgment of which one is a better candidate over another. Let us start with spins, because the spin is the most obvious fundamental two-level system in quantum mechanics. And this is a property of fundamental particles, for instance of electrons, but also of the particles in the nuclei, so nucleons. So these are then indeed suitable candidates for quantum information processing applications. And so, for example, when one first implemented the Shor algorithm for the factorization of the number 15, this was then indeed achieved using nuclear magnetic resonance on certain molecules. And in these molecules, the nuclei served as the quantum bits, and even though there was a very small number of them, this was enough to factorize this number 15. Now, one of the strengths of this nuclear spin is that they're very well defined and relatively well isolated, but this also means that they are very difficult to manipulate, and also it's very difficult to scale the system up to a larger number of nuclei, in particular because they are so weakly interacting. For instance, there aren't any easily accessible molecules where you would have a very large number of them. Now for electrons, their spin can also be manipulated, again with magnetic fields, and this can then be done both for electrons that sit at a certain place or electrons that move around, for instance through a semiconductor. And indeed there is a whole research field which is known as spintronics. The strength of these spin states is again that they're very well defined, and on top of these electronic spin states interact much more easily, also with other spins and with the environment. But on the other hand, this means that these systems are very difficult to isolate. There will be other electrons in the environment that might also be moving, and they generate magnetic fields, and so there are lots of uncontrolled interactions involved in this. Indeed, the applications of spintronics so far are mainly classical ones, very similar to what we have for electronics, the counterpart based on the charge of the electron, which we exploit in normal computers, which also actually involves quantum effects, but not of the kind that we can exploit for quantum computation. So for instance, we are not operating on individual charges in here. And this brings me down to this point here. So we could, for instance, use the electronic charge, or also other charges, for instance, those of ions. Well, for electrons, these charges are indeed very easily manipulated from the outside, for instance, using gates, but these charges also interact very strongly with all the other charges in the environment. And with this, we really have progressed to the opposite end of the spectrum, to systems which are very easily manipulated, but also interact very strongly with the environment. So they are very difficult to isolate. Well, then we have these ions, which are also charged, but they can be nicely isolated by using so-called traps, which utilize electric and magnetic fields. The quantum states that one can exploit for these ions are, for instance, motional states in the trap or atomic excitations. And these are indeed then one of the systems where the progress so far is most advanced. And one of the key questions then is perhaps how to scale this up to larger systems. So let us move on to photons. Well, for photons, one exploits, for instance, the polarization degree of freedom, which is mathematically equivalent to the spin degree of freedom. And now this gives us again a very well-defined two-level system, which on top of this is extremely well isolated. For instance, two photons do not interact. So this is a very clear strength. We have a very well-defined and isolated system, but there's also an obvious weakness, namely when you think about how to implement a 2-qubit operation such as a controlled NOT gate. This means that we should make these photons interact with other quantum systems, such as the mentioned ions, but more generally perhaps atoms, and this indeed leads to the idea of cavity quantum electrodynamics, in which one uses both atomic states as well as photonic states. And the key idea would be to place one individual atom in between two mirrors, forming a certain cavity. So we would have an atom here, and we consider two different situations. Where the atom is, for instance, in some excited state. So these are the atomic states, and it might be in this excited state, or it might be in the ground state. But then it has released this energy in the form of a photon. So these would be the two different states that form the quantum bit. This quantum bit can then be manipulated, for instance, by sending additional photons into the system. And on top of this, one can use this mechanism, these atomic states, to effectively make two photons interact. One can use atoms also in many other ways. For instance, when one cools down an atomic gas to very low temperatures so that it starts to behave as a collective quantum system. And this indeed has many applications in general in quantum technologies, including that one can use this to simulate other quantum systems. Now, such collective quantum effects are also at play in these superconducting devices. And these superconducting devices are very flexible. For instance, they are allowed to realize quantum bits in 3 different ways, where one either uses the magnetic flux, which also is quantized in quantum systems, or individual charges confined to certain regions in these devices, or indeed also the phase difference of the corresponding macroscopic wave function, which features, for instance, in the Josephson effect. So these are very flexible devices, and one can also easily control them from the outside using electronic components. And such electronic components can also be employed to make these devices interact and to read out the information. And this can also be in principle scaled up to very large systems. But these are fabricated systems, and therefore one has to manufacture all the components very precisely, and then the system needs to be isolated very well from the environment. Nonetheless, this is again one of the platforms where a lot of progress has been made already. This concludes this little overview over possible physical platforms for quantum information processing. And with this, we also come to the very end of this course. For me, quantum information processing is fascinating for 3 main reasons. With its deep concepts, it teaches us a lot about quantum mechanics. And it utilizes these concepts in very concrete ways to come up with ingenious solutions for very important problems. And finally, it challenges us to find ways to realize these systems in practice. I hope you also took something interesting or useful away from this course. For instance, just the idea that there must be so much more interesting stuff to explore. And this is definitely true, and for this and everything else, I wish you all the best.